So our topic today is this one, okay, about the probability of accidents and return period for building, bridge, and dam. Okay, but before we move to this quite advanced in terms of the seismic and earthquake engineering, so most of my students has covered and have a knowledge about seismology, how to get the earthquake database, and how the earthquake come from the fault line. All these the seismic loads coming from, and how these seismic loads would affect to the buildings. So this is before you come into this, I'm sure that most of you has already know a little bit knowledge about seismology and earthquake database and earthquake engineering, right? Um, okay, so before I start, okay, most of my lecture I will refer to this YouTube. Okay, this is I want to promote to you guys. Okay, because this is very useful and very informative YouTube channel. The first one I refer to Part Year One. This is made by our my friends, yeah, tadi moderators, our moderators, Dr. Nis, Dr. Iwan. This is his YouTube channel. You may go to this name Pak Iwan, and you can subscribe. So all of the knowledge on how to do analysis, for example, the static loads and dynamic loads, are explained in this channel. And another second channel that I usually refer to is this Fawad Najam. And this is explained about all the seismology, the earthquake from static, from the basic level until the advanced level. So if you want to know more on the basic of earthquake seismology until the advanced and also using the software analysis, you may refer to this YouTube channel as well. Okay. Okay, so my lectures will be has a three section for today's lecture. So I would try my best to explain this three section within 2 hours our lecture today. So I will go the first one on the introduction, okay, some of the interesting facts about earthquakes, and we will go to what is the types of earthquake hazard, and we will go on the definition on the seismic hazard. And then on the second section, we will go to the ground motion parameters. So most of the building, when designing a building with seismic load, they're usually referred to this ground motion parameter that will be based on the hazard analysis. And we will try some example using the simplified PSHA. PSHA is from the probabilistic seismic hazard assessment. And then the last section will be more on the earthquake resistance design, that what is the criteria that we usually tackle for building, bridge, and dam. So our first section will be on the earthquake facts. So in around the world, so this is the record that been published by this person, okay, in 2021. So if you see the graph, kita nampak sangat lah, tapi boleh tengok the chart, the death from earthquakes. So this is the record since 1500 until 2017. And we look into this, this is the year and the total of death. So the total of deaths, we see that it keeps increasing decades by decades. Okay, and since 1500 years until now. So in statistically, so we can say that 20,000 people are killed every year, okay, by this natural phenomenon by the earthquake. Okay, because of the 20,000 people killed per year. Why? Okay, if you see and look into this map, it is a very colorful figure here. It's showing that this is an earthquake event collect from 1904 to 2014 by this guy. So if you look into this, so there are so many epicenters, okay, earthquake from the moderate earthquake 5.5 until 9.5. Okay, okay. So if you look, see over here is the earthquake happen in this very densely populated. Okay, there are so many earthquake happen here. We are here kan, kita kat sini kat Malaysia ni. So we look into this. Actually, the earthquake happened since that 1904. So means that earthquake happen if you learn about the plate boundaries. Plate boundaries is the movement between plates. Okay, so most of these earthquake, the big earthquake, moderate to big earthquake occurred on these plate boundaries. Okay, and some of the part will be a no earthquake, but if we move much more closer to the plate boundaries, the earthquake is much more active. Right. So, and then this is the interesting earthquake facts. Dangerous earthquake location. This is actually I collect from this person. A new mapping project, 10 years in the making, found that Japan, China, Philippines, Iran, and Indonesia are among the 15 countries that could be labeled as dangerous earthquake location. Labeled as dangerous earthquake location, okay, because it's these 5 countries are among the active earthquake activities. So if you look into this Asian region, so we have most of them is from Asian region, but we are um, neighbor, our neighbor, Philippines and Indonesia is quite close to us. Okay, and we should be aware the earthquake that coming from Philippines and Indonesia. And about the fatalities, so some cases, if we look into the active regions, we know that the building must design on the seismic loads because it will create some damage to the structures, right? But nowadays, we see that when we have just a small magnitude or minor earthquakes on a certain area, that also can create a heavily damage to the structure because of the structure is not designed with the designed to withstand the earthquake loads. So many like the earthquake can cause structure to collapse if they weren't built to survive earthquakes. Okay, the severe shaking can lead to higher earthquake fatalities. So if you look into our Malaysian condition, we are categorized low to moderate. If we are stable but no earthquake, then we are safe. But we are stable with low and moderate earthquake. So in this case, we don't know how much earthquake will happen in the future, but we have the statistics. So what we do is we have to design our buildings based on with the building that can survive from the earthquake shaking that can reduce the losses of human life. And this is another earthquake facts. So what is the greatest earthquake ever happened in our world? So in 1960, it's happened in 1960 in Chile. So the magnitude is the highest ever recorded, which is equals to 9.5 magnitude. So it's quite high, and this is, I think, the most.
Sorry, Dr. Sheena. Dr.
Yes.
Sheena, sorry ya. Saya nampak ada komen dari chat ni. Slide kita nampak kabur lah. Macam mana nak buat ya?
Oh, okay, 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 okay. Oh,
Saya
saya
cuba.
lupa letak setting tadi. Okay, okay.
Okay, sorry ya. So, saya pelik semalam elok je.
Itulah. Saya terlupa
Okay.
letak punya apa tu, animation. Sorry ya. Sekejap. Webex ni dia ada setting dia ada banyak sikit. So
Okay.
kalau motion, so kena klik option motion. Okay, now clear? Now clear? You nampak?
Cuba kejap sikit lagi. Macam ni lagi, macam belum jadi lagi.
Macam masih blur?
Blur lagi. Tulisan dia macam tulisan Tamil.
Sekejap. Kenapa? Text and image tu. Okay, how about now?
Okay, good, better. Thank you. Dah nampak apa font apa.
Alright. Rasanya tadi untuk video.
Arial.
Okay, alright.
Okay, thank you. Okay, thank you for the comments.
Okay, so this one is just the earthquake facts. Okay, sebelum kita go to section berat-berat sikit. Right, so the first one is the greatest earthquake happened in Chile, okay, in 1960, with the magnitude is 9.5, the largest ever recorded earthquake. And then what about the highest number of earthquakes? So we have these two locations, okay, so from USGS, two locations, which is in Japan, another one is Indonesia, are the two countries with the highest number of earthquakes. Indonesia is our neighbor, okay, so it's quite close to Peninsula, right? So this is we should tackle on, and we should be alert lah, because Indonesia is the highest number of earthquakes, okay, and these two countries has record the tsunami in a few years back. And what's the terms of megaquakes? Megaquakes is actually the highest earthquakes, which is magnitude of 10. So magnitude of 10 is called as a megaquake or higher. So theoretically, it's impossible, okay, by the scientists. This is actually we cannot achieve until magnitude of 10. Because because the earthquake method we calculate based on the fault line length of the fault line. So the fault line length is not capable that we have now in our world. Is not being capable to produce the magnitude 10. So okay lah, means we are glad to hear that we cannot, because 10 is the most and higher magnitude which can severe damage to the buildings. Okay, and then the casualties. Okay, most of the casualties between magnitude 9.4 to 9.6 is can kill people and will injure thousands of people in the city and around that city. Okay, that's close to the city. So it's very dangerous earthquake if we have this type of magnitude of 9.4 or until 9.6. And probably you know about earthquake, but it actually has several types of earthquake hazards. So the first one, we normally say that earthquake produce shaking, earthquake produce shaking. So this is actually one of the types of earthquake hazards. We feel the shaking. Okay, we are inside our house, and once earthquake coming, we feel the shaking above the ground. And then surface rupture. In many places, they are producing this surface rupture once the earthquake coming. And on the surface, we can see there are holes ataupun displacement between the surface area. So we can see some displacement, once go up and once go down. So this displacement that produced by the earthquake, we call as a surface eruption. So this is due by the earthquake. And then we have ground failures. So normally the ground failures, we are coming, are the effect from the earthquake. The earthquake shaking, and then suddenly the soil is liquefied, means it cannot sustain any load, it's turned into liquid. And then it will create sometime in the hillside where there are not strong or unstable embankment. So they will produce some landslide, mudslide, and some differential soil settlement. So this is the effect that if we have an earthquake. And then tsunami. Okay, tsunami is due to the sea level coming from the fog under the sea. So this is happen once there are displacement in the sea, and it will produce this huge wave. This huge wave and coming to our seashore and will create damage to the building as well. And floods. Okay, if we have dams, if we make a dams or dams lah. Okay, so if we have an earthquake and damaging the dams, it will create floods in some other places that close to these dams, and fires, okay, resulting from earthquake. If we have earthquake that happen, and if the structure has something that, for example, power plant, so it can easily catch a fire due to this earthquake vibration. So this is just some photos of types of earthquake hazard, and this is the case of Herayani city in Sulawesi. The magnitude is 6.2. This is due to the ground shaking hazard. The ground shaking hazard, you can see this is a house, I think a 3-story house is badly damaged due to the earthquake. So this is total loss. We cannot, this, the structure is badly damaged. Okay, we cannot see any structure here. So the beam, the column, all damaged already. And this is another one. Okay, we can see some of the houses is badly damaged. Some of the structure is still standing. If you look into this, okay, this ada orang lagi ya, sitting on this house. Even though this structure is already badly damaged, but this structure probably has some moderate damage to its structure, such as on the wall and on the column side. And this is surface rupture hazard. Tadi kita shaking, earthquake shaking. Okay? So this is the type of surface rupture. Once we have earthquake, the surface of the ground will displace. Okay, this is example from Shikang Dam in 1999 Ichi earthquake in Taiwan. You can see that this is the dam has damage on this side. Okay, because the fault line is over here. Okay, the fault line is over here. So we can see once the surface structure hazard happen, so it's caused a displacement some of the area. So one will go up, one will go down. And if you look it closer, this is the this is the level, okay, the original level. Original level. So you can see this side has been lifted up by 8 to 9 meters, go up. So we cannot see the fault line over here, but from this pattern of structure, we can say that one ground surface here goes up, and this remaining at this level is still here. So it is considered very dangerous if we build dams exactly on the fault line. So in our to reduce the loss by the earthquake, our structure should not be built on top of the fault line. Because we should avoid that, and also we should avoid our structure to be built close to the fault line. I think this is the case when they do not know about the fault that have under these dams, so they just build this dam, and then once the earthquake happens, so this is what happened, right? Okay, this is just a repetitive from that. Okay, ground shaking caused vibration in them. Okay. And then fault movement in the dam foundation or movement along discontinuities in dam foundation near major fault, which can be activated during strong earthquake, causing structure distortion. And this is due to the soil liquefaction. This is a picture from the Hokkaido Uduru earthquake of Japan. So once earthquake is happened, sometimes the soil has lost its strength. So it's lose its bearing capacity. So it cannot sustain the soil become liquefiable. So once it happened and liquefaction happened, so we have to demolish this building lah. Means that here the location is not safe for people. And then another picture, okay, showing that liquefaction hazard. Okay, this house is already wants to go this side. Okay, it's rotate. But this house is standing. Only this area is having the soil liquefaction. Okay, this is due to the earthquake, not from the normal soil settlement. This is from the earthquake. Once the earthquake is shaking this area and the soil liquefaction happens under the house. And then earthquake can also trigger landslides. So this is the case from Wenchuan earthquake in China. So they built their buildings. Okay, they are so moderate stories of building, I think. So you can see there are badly damaged due to the soil settlement. Okay, the soil from the earthquake and then landslide happened. So it moved to another places. Okay, once the landslide coming, earthquake coming, and then landslide is induced. So you can see that all the house are going into a new place. So they have to be scenic. So this area is not safe. You can see there are so many landslide happen in this 7.9 magnitude. And this is because of the unstable soil and for this hilly site. If we do not prepare some stable embankment in this area, so once earthquake is coming, it's not safe for the people to live beside this hill. Okay. See, their total loss also would be increased lah. You see, so many houses involved, and will involve so many loss of life. And also, earthquake can trigger tsunami as well as fire. So if we have buildings that store very explosive material, it can create fire. And this is actually a picture from the previous Japan 2011 with magnitude of 8.9 that caused the tsunami. You can see there's water. And this house has been moved from one place to another place. Sudah hanyut. Okay. And some of the area probably stored some of um, which can catch fire easily. So it will create some explosion to this area. So will be create a highly damage of structure as well as many total loss of life if we not prepare, and economical is it costs very benefit. Itulah banyak kita akan pakai kerugian lebih banyak lah. Kerugian. Sebenarnya term tu saya dah lupa. Right, so here is actually frequently asked question. Okay, normally I find this as well. If normally I give talk to people and they will usually ask this question. So the first question is about where will future earthquake occur? Okay, normally we don't know where will future earthquake occur, but if we trace back our previous recordings, 100 years, 200 years, 300 years, and very good one is 500 years. So we can see this pattern of earthquake, and we can know where this earthquake will happen in the future. Okay, based on the trace record on the past historical data. And then what will be their size and their frequency of occurrence? So the size is based on our database as well. So if we trace back our historical data and we have to look into how has this area has created which and highest magnitude. Okay, for example, in Rana we have 6.0. So this is will be the earthquake, largest earthquake, and 6.0. So probably in the future, we have to increase our design up to 6.5 in order to know that this 6.5 will happen in the future. And the frequency of occurrence, so how many times this 6 magnitude will happen in the future. So we have to look back our trends of data, historical data. For example, 100 years, between 100 years, 50 years, 30 years. So we have to look back how many times this earthquake coming will be in the future. So we can have only based on estimation. So, but for big earthquakes like 8 and 9, it's considered as a rare earthquake. So rare earthquake probably we take as 50 years, 50 years of occurrences, between 50 years occurrences, something like that. And the third question is about what will be the ground shaking intensity at the site produced by earthquake of different size, focal depth, and epicenter location. So the ground shaking intensity, so we have to look under the modified Mercalli scale. So once the earthquake coming, so we look our structure is badly damaged. So the intensity would be 6 to 7 or 5 to 6. So this is will be the MMI scale is our standard form. So we should measure our intensity based on our structure that has damaged by the earthquake. Then the next question on how will the ground motion be influenced by local soil conditions and geology. So the ground motion is actually the earthquake loadings lah. Okay, normally we have earthquake loads from prediction from the seismic hazard assessment, but due to the local soil conditions, we have to refer our building code that have the amplification factor. So the amplification factor, so we have to times with the amplification factor based on the type of soil, so that we can have the ground motion that will be based on the different type of soil. And then what will the earthquake hazard landslide equation produce at the site? So this is, you can done some simple study or literature around that area, or just make a sample that happened. Is there any record that this area has produced some landslide and liquefaction? We can actually calculate some of these hazards, okay, for the landslide, just a small calculation, and predict is there any landslide in that area. Okay, so it can be based on the visual observation as well, or from the theoretical. And then lastly is how about the susceptibility of building and structure to damage from the ground shaking and ground failure. So this is based on the vulnerability of the buildings, whether the building can survive or not from the earthquake. So, but this is based on the vulnerability assessment. So most of the analysis is we have to do some analysis using software in order to check our building is can able to sustain from quick loads, and also we can do some visual inspection to the building. So this is actually the I would say the equation. Normally, we how we calculate disaster. So disaster is actually equals to hazard times the vulnerability and then times with the exposure. So the hazard is not natural or man-made phenomena. It can be earthquake or man-made means that explosive. So the shaking from explosive can be one of the hazards, and other type of hazard lah, like floods, um, floods or wind, something like that lah. Okay. Then the vulnerability is if we lack of resources of community. So the greatest benefit can be achieved is we have to reduce the vulnerability to hazard. So if we lack of resource for communities or we have the buildings that are built in inappropriate, so the vulnerability will be high. And then the exposure is how people know about this hazard. So normally people don't know about this hazard. So this is the exposure lah. So we have to make people know about the earthquake in our area. So the disaster is actually a sudden accident of natural catastrophe that cause great damage or loss. And this hazard and vulnerability is actually the risk. Okay, so how can we reduce the risk? To reduce the risk of disaster and increase safety, so we need to estimate our hazard, so our hazard properly in order to reduce the vulnerability. So if we manage to get some data of hazard, so suitable of seismic design loads, for example, so we can make a building that's safer to people. So it will increase the safety of the buildings. And we can also make exposure to people and increase awareness to the people so that people know about the risk they will get, okay, coming from the natural hazard. So we go to the next on the seismic hazard definition. So yang ni part dia a bit tough sikit lah. So we will start from the seismic hazard definition first. So the seismic hazard, so saya punya putih-putih lah. Hopefully you can see. Okay, seismic hazard is the probability that an earthquake will occur in a given geographic area within a given window of time and with ground motion intensity exceeding a given threshold. So it can be used as a probability or deterministic. Probability, so we have to capture all the earthquake situation in that area, so we can predict within 100 years record or 500 years record, so we can know what will be the seismic hazard in that area. Then seismic hazard assessment, SHA. So normally we use the seismic hazard, we assess in terms of seismic hazard, can address any natural hazard associated with earthquake, including ground shaking, fault rupture, landslide liquefaction, and tsunami. Then most interest is in the estimation of ground shaking hazard, since it causes the largest economic losses in most earthquakes. So ground shaking hazard is due to vibration. Okay. So normally we use the estimation from the ground shaking hazard. Then ground motion is the predominant cause of damage from earthquake, building collapse, dam failure, landslide liquefaction are all the direct result of ground motion. So what is ground motion parameters? So there are many different ground motion parameters. Sometimes they use as a displacement or velocity, acceleration or spectral acceleration, as well as MMI. And all of these five, we normally use a peak ground acceleration. Peak ground acceleration is one to be the most usable or considered and preferred ground motion parameter in this seismic design analysis. So seismic hazard is ground shaking hazard or the probability of occurrence of potentially destructive seismic ground shaking at a given site within a given time interval. And this is about 10% probability of accident in 50 years. So means that this is corresponding to the ground shaking hazard. That probability at a site in 50 years while experiencing PGA more than 0.1 G is 10%. I will explain more on these terms later on, but only this one, only the terminology lah. And 50 years is actually the exposure time. So if we make some illustration of our structure, so our structure will shake on this horizontal. So this shaking, we normally get the loads of seismic in terms of ground acceleration or peak ground acceleration. So the inside our building, uh, force of our building will be equal to mass times acceleration. So the mass is coming from our building. So the acceleration is coming from our peak ground acceleration or the seismic loads. So this is we call as a design ground motion parameters. And these different building codes will provide the ground motion parameters or input required to calculate the factor of earthquake force, and those input is the function of PGA. So this is the acceleration that we have, right? Yeah. So this is in terms of peak ground acceleration. Okay, this one, and this one is in terms of the velocity, peak ground velocity, and this one in terms of peak ground displacement. And the peak ground acceleration is the index of seismic loading. And this one use the terms of GAL. The GAL is 980 GALs is actually equals to 1 G.
Okay.
So here we are again. We measure the seismic loads based on its peak ground or ground acceleration. So in a global seismic hazard map, this is one of the outcome coming from the seismic hazard assessment. Kalau tak short form di sini, SHA is actually seismic hazard assessment. And if you look into this map, so it's categorized with zones. So zone 0, zone 1, zone 2, 3 until 4. And this map is with an accident probability of 10% in 50 years, equivalent to return period of 475 years for medium subsoil condition. So it means that the 10% is the chance for the earthquake will achieve certain PGA more than this PGA will happen in the future. So it means that 90% would not happen lah. So the explanation will explain later on. And about this zone, if you can look into this area is categorized as zone 0 to 1, and some yellow area is zone 1, and the red area you can see here is zone 5. So from this here, you can see the color is actually the red one is the highest PGA value, means that the earthquake shaking, the seismic load is higher. The acceleration is higher. So it can be 0.4, 0.8. And normally we found this on the area where it flows very close to the active fault line. So you can see here for Indonesia region and Philippines region also has the zone 4 and below. And this one is we interpret on, we can see that how where is the area which is under high seismic zone, high seismic activity or high seismic zone. So we can look this map to look into how big is intensity within that area. And if we focus more towards our Peninsular Malaysia, okay, so contohnya kita ambil dekat okay, this Kuantan. So we know that it's equals to 3% of G, means that equals to 0.03 G. So the maximum or the acceleration value for Kuantan is equal to 0.03 G, means the acceleration is equal to 0.03 G. So the map is showing the contour, okay, in the unit of percent of G, means this map is for 10% probability of accidents in 50 years exposure period, means that 10% that earthquake happen in the future more than 0.03 G will be 10%, whereas 90% will be less than 0.03. Faham tak? Okay, I repeat again. 0.03 G of this maximum acceleration for this quantum area. When there are 10% probability of this value, PGA value more than 0.03 G will happen in the future. So it is equal to 10%. So 90% will not achieve 0.03. So 90% will be lower than 0.03 G. So this is the expected maximum acceleration value for this area. So we can use this maximum acceleration value inside our building design. So the 50 years exposure period, normally we in designing building or other structure, normal structure or dams or bridges. So we use this exposure time of 50 period. Means within 50 years, the building still can survive. Yeah, within 50 years, that the 10% probability is exceeding, the probability of exceeding is only 10%. Okay, if 10% achieving more than 0.03 G. And in the Hunter seismic hazard assessment, we have two types actually. One is using as a probabilistic or deterministic. Only two types. So the first one is DSHA. DSHA is a deterministic seismic hazard assessment when we consider only single scenario. So we have fault line that are closer to our site and this fault line that produce the highest magnitude, and we will calculate based on one source only. And we calculate each of these seismic sources, and we will calculate what will be the maximum peak ground acceleration based on these seismic sources. But we only pick one value, which is the maximum one. And then the next second type of seismic hazard assessment, which is a probabilistic seismic hazard assessment or PSHA, is we tackle all the parameters of the fault line, the magnitude, and the recurrence of the earthquake database that related to this area. So we have to calculate all the possibility of fault or seismic or earthquake under this area. So we perform and combine all the parameters into one. That then finally we'll get the background acceleration. So this also means that the deterministic is a subset of the probabilistic methodology. It can be one of the methods, small method, deterministic, and then we advance deterministic analysis, and then we include in the probabilistic analysis. So this is the general information or general method, general steps in order to perform the seismic hazard assessment. The first step is we have to look into our earthquake source. Okay, from the fault line, okay, the type of the fault line, the focal depth of the fault line, and the database of our site of interest, the magnitude, and how far the earthquake will be produced from each of these seismic sources. And then we do the analysis using the recurrence rate. So we have to collect the data. For example, we collect the data for 100 years, 200 years, 300 years. So we combine all this data and then do the recurrence rate analysis in terms of the number of events per year versus the magnitude. So one magnitude per 3 will give one rate of occurrences. So one magnitude and different magnitude will give different recurrence rate. And then the third one is the attenuation. So the attenuation is how the energy of earthquake will be attenuated when subject to distance of 0 kilometer until 1,000 kilometers. So how it will reduce its acceleration from the focus point until the end of the site. So their attention function is based on the mathematical equation. Normally we use the terms as the attenuation, and some analysis the terms is changed into ground motion prediction equation or GMPE. Then starting 2020, the terms again changed into ground motion model. So all of these are the same thing. So this is only to do the analysis or based on the attenuation function. And then finally, we do the analysis and we'll get the hazard curve. Okay, the hazard curve is the curve, the plot of the probability of accidents versus acceleration. So this one is, I will show you this example. Okay, for example, we have, next thing. We have a peak ground acceleration, for example, 0.1. Okay, here in this black star, 0.1 G, okay, is produced for one side, and then we see that the source to distance of this magnitude with the magnitude of m prime. So we can know that, for example, this is 50 kilometers. So 50 kilometers of earthquake with magnitude m prime has produced these numbers of peak ground acceleration, which is equal to 0.1 G. And then this magnitude m prime, okay, with that producing this PGA, peak ground acceleration. So we can know that how much is the rate of accident, means how is the probability of this earthquake happen in 1 year. So we can plot into this graph. So this means that this is a cumulative annual frequency. So 1 year, how much is the number of events for 1 year for this magnitude? And then from the annual rate of accidents or probability of accident with this event, okay, number of event per year. So we can now plot into our hazard curve. So the hazard curve is the plot of annual frequency versus peak ground acceleration. So with this value, we plot under here, and the peak ground is this PGA black star is equals to 0.1 is here. So we can plot every peak ground acceleration with the rate of event 1 year, so with different magnitude. So we will have one curve of hazard curve. So jadilah dia punya curve macam ni lah. So every point will produce a different PGA and different annual rate of accident. So we try to do one example. Okay, this is just a simplified passage in order to understand on this the terminology on how we get the probabilistic dual motion estimation. So imagine that we have a seismic source A, and we are here at this site, and this location is with distance of RAT. Okay, distance of RAT. So this side to this seismic source where the earthquake happened. So the distance will be RAT. So we assume that the distance of our site to the seismic source is 30 kilometers. Okay, and then we plot these two graphs. For example, we have six magnitude of earthquake. So we just plot this 6 magnitude under this graph. So this graph is coming from the recurrence relationship for seismic source A. So from that seismic source A 32. So we plot how is the event per year. So how much event per year for magnitude 3, magnitude 4, 5, 6, 7, and 8. And then we plot into this graph. So we get finally into this graph. And then we look into magnitude 6. So what will be the cumulative annual frequency, which is event per year? So we just go to this side. Oh, tak straight pula. Okay, itulah kat sini lah. So this area, so means that the event per year is equal to 0.08, something like that. Yang ni adalah in terms of the 0.10 to 1. The scale is using the log distribution. And then because our distance is 30 kilometers, 1, 10, 20, 30. So 30 kilometer with magnitude 6. Okay, so this one is plot based on the GMP or attenuation, a graph of attenuation. So we can say that the 30 kilometer distance with the magnitude of 6. Okay, 6, 5.5, 6 or at the middle. So this is based on these two equations. We just assume that this is the location for our distance of 30 kilometer, and then if we go to the left, so we can say that the peak horizontal acceleration or peak ground acceleration value that's produced by this 6 magnitude of earthquake with distance of 30 kilometer is equal to 0.07. 0.06. So 0.06 G. Okay, with that happen on that side, so we will receive the peak ground acceleration within 30 kilometer away and with magnitude of 6. Faham lah. Okay, we try another example. Okay, let's say that if we have PGA level at the site of interest is 0.1 G, and then we plot the 0.1 G For example, here we say that it is 6.6 magnitude. 6.6 magnitude. So we plot one line here into this graph of 6.6, and then we go down. Oh, nanti repeat tadi lah. Okay, repeat tadi. So 10, 20, 30 kilometer away is with the magnitude of 6.6, we'll get 0.1 g of acceleration. And then if we plot into the cumulative annual frequency, means that in 1 year, how is number event for this type of earthquake? For example, we have a magnitude of 6.6. Okay, using this chart, 6.6 magnitude, and then we plot using this graph annual frequency. And then if you go left, it will be equal to 0.07. So if we 0.007 event. So this 0.007 event means in 1 year, the magnitude of 6.6 will happen with 0.07 probability. Okay, the 0.007 event per year. So in order to this earthquake coming in the next year, so the probability is 0.007. So the 0.07 event per year is actually the annual accident rate. So if you have 7 magnitude, so you have to plot 7 into this line and go left. So you will get the value. 1 year, how much will be the number of events? Now we have 6 magnitude of event with the probability in the next year is 0.007. Okay, if we collect all the database and we say that the total number of event or annual accidents rate is total number of event divided by the time period. So this 6.6 magnitude will happen in the future is 0.07 in next year. So this is this arrow showing the earthquake event with PGA more than 0.10 G, because we interest only 0.01 G. So in next year that happened in that area 0.1 G. At that site, the annual accident rate will be equal to 0.07. So if we calculate for in the future for 10 years, so you have to times the number of events 0.07 times with 10 years ahead. 10 years ahead, so you will get 0.07 in 10 years. So if you translate into percent, it will be equal to 7%. Or you can say that it is 7% probability of accidents in 10 years. So the probability that the earthquake more than 0.0 G happen at this site will be equal to 7% in 10 years. For PGA, 0.1 G. Now for the return period, it's a reciprocal from your reciprocal of this number of events. Okay, for example, return period is time period divided by total number of events. So our total number of events is 0.07. Okay, so means that if we have in 1 year, 1 year reciprocal from this probability of event in 1 year, so the reciprocal will be 1 divided by 0.007. So the return period for this PGA of 0.1 G will be equal to 143 years. Okay, pening. Okay, so there are different form hazard ke, tapi saya akan tengok balik lah. Saya rasa macam kamu nanti pening pula. This one, this actually how we translate the probability of accidents and how we translate the return period. The probability of accident is actually percentage. Okay, percentage that how much PGA will happen more than the expected PGA in the future. So for this case, the earthquake event with PGA more than 0.1 G that happen in the future will be 7%. Okay, in the exposure time is 10 years. 10 years is exposure time. Okay, it can, but normally we use 50 years for the exposure time of our buildings. Right. Then for the return period is the reciprocal for our event per year, which is 1 over 0.007. So it will translate directly, it will be equal to 143 years. So either you may use in terms of probability of accidents or the terms return period. So both are the same. So there are actually different forms of hazard curve. Hazard curve is coming from the seismic hazard analysis explained earlier. But this is the final when we done the seismic hazard analysis, and there can be different form of hazard and hazard curve. For example, here we calculate as an annual rate of accident or how much event per year in that area. For example, we have 0.1 G here. So how much will be the annual rate of accident? So what will be the number of events per year? So for this case, 0.1 G, number of events per year is equals to 0.002. But if we translate into the event per 50 years, so you have to times 50. That is to 10, but we interest in 50 years. Exposure time is 50 years. So you have to times 0.002 times 50 will be equals to 0.1. So this is the rate of accidents in 50 years, okay, which is equals to 0.1. Okay, the same also here it's equal to 0.1 G. Or it can translate into percent, okay, 10%. So it is timed with 100%. So we get 10% or in terms of the probability of accidents in 50 years. This is units percentage and this is 0. So these three usually we use for the hazard curve. But for my usually my analysis will use in terms of percentage or rate of accident in 50 years. And this is example of seismic hazard map of Sabah. You can see that dalam graph tadi tu, okay, this is 10%, right? If we have below than that, means that if we have 2%, so how will be the PGA value? Is it going to be higher PGA value or lower PGA value? Or 1% or 0.1%? Nak dia tidur dah tak? Okay, so if we have 2%, okay, here, the PGA should be higher. 1% even higher. And if we have 50%, we'll get much more lower PGA. So 2% will be give you higher PGA value in comparison with your 10% of probability of accident. So this is a map totally. Okay, just this showing the 10% probability of accidents in 50 years. Okay, the map showing the color, the concentration on color. So the more concentrated color will be give you higher PGA. And the difference between 10% to 2%, 10% you can see that the PGA is much more lower compared to the 2% probability of accident. Because 10% probability of accident is for normal building, we usually calculate based on 10% probability of accident. So it means that the PGA value will be more than this PGA value is 10%. So equals to 470 years return per year with 50 years exposure time. Then if we have some sensitive structures such as bridge or plant or building that close to the fault line, so we may use 2% probability of accidents. And if we translate the probability of accidents that happen in that particular area with this PGA value, that will achieve this PGA value is 2%. So the difference 10%, 2%, 2% if we has a rare event. For example, in 100 years, that area will have a magnitude of 7 or 8. So that's why we use 2% probability of accidents because of the rare event. Okay, and then higher magnitude of event would be give you a longer return period. So assignment for this, I will give this assignment to my students and to UNIMAP and UMP students. So it's based on depends on your respective lecturer. Okay, if they want to use this as your assessment or not. But this question, you have to do it for my students. Okay, for a engineering class, KA 47803. So you have to submit this assignment to me, hard copy. Yeah? For this assignment, you have to choose, let's say you have the PGA is 0.2 G with method 5.5. So you have to determine what will be the PGA level. And so you have to calculate the probability of accident in 20 years. So it means that the number of events per year, you have to times it 20 years. And then determine its return period. So reciprocal from the event per year is 1 over event per year. So you will get the return period. Okay, boleh? Alright. So then the second assignment. So tadi tu 0.2 G. Okay, so yeah, 0.2 G. So you have to repeat again for other cases of PGA level. And then you have to identify the PGA at DBE and MCE. So actually the DBE and MCE, DBE is a 10% probability of accident. For example, if we have 10% the number of event somewhere here. Okay, so this is we call as a DBE. So, but we don't know what is the event per year. So you have to identify. This DBE is actually equals to 10% probability of accidents. And then MCE should be much more higher PGA value, which is down here. MCE will be equals to 2% probability of accidents. Okay, so what will be the annual rate event per year? So you have to identify the 10% and 2% MCE and 10% DBE. So DBE is design based earthquake, and C is the maximum caliber earthquake. Just now the example is for one source. So what will be if we have more than one source? So example, we have a seismic source at A, B, and C with different distance. So what we need to do is to combine all these annual rate of accidents with the total on this side. So we have to combine the annual accident from source A, from source B, and source C. So that we can get the final rate of accident around this site. So this is what we done using the probabilistic analysis. We combine all the statistical parameters, then we get the rate of accident at that area. And this is actually the simplified form of how we get the probability of accident. Study how to translate 10% to 500 years or 475 years or 2% into 2475 years. So the G is actually the unit on the acceleration due to Earth's gravity, and 1 G equals to 980 gal. So if we use this equation, CR is the return period, okay, which is, for example, 145 years, 475 years, or 475 years. And the Q is percent probability of accidents. So we interest in 10%, 2%, 1%, or 50% probability of accident. And T is exposure time. So for example, if we have T exposure time is 50 years, and we only interest in 10% probability of accidents. So you just put the numbers into this equation. Return period equals to 1 over 1 minus 1 minus Q. Q is 10%, and you need to put into number 0.1, and into the power of 1 over T. T is exposure, time which is 50 years. So 10% probability of accident is equals to 475 years return period. Now you may try for Q is equal to 2% or 1% and see how much the return period for these two probability of accident. Okay, so this is only on the general information that what we use for the ground motion parameters. So normally we use three: peak ground acceleration, peak ground velocity, or spectral acceleration. So traditionally we have used for our building using the peak ground acceleration, okay, which based on the 0 second of PGA. And sometimes they use the design loadings based on the peak ground velocity. This is a good index to hazard to taller buildings, but it is not clear how to relate the velocity force in design a taller building. And nowadays, they use RSA. So RSA is a response spectral acceleration that involved within the certain period of buildings, or not using the 0 second period, but they use a short period or long period. So normally they prefer for low-rise building is a short period spectral acceleration, and for higher or moderate level building, they use a longer period acceleration. And while PGA is what experienced by particles, SA is approximately what experienced by a building. So it's nothing. So the SA is the maximum acceleration experienced by them. And we know that the maximum earthquake force in building is the building mass, total building mass will be times with the spectral acceleration. And this one is use of I think kita dah section 3 ni. Cuma tak keluar saya punya. Okay. This is actually dah masuk the last section. So for building, we usually refer our building common building design code. For Malaysian region, we have our own Malaysian annex code that what will be the earthquake building earthquake resistant design that's suitable for our building. So we use either DBE or design based earthquake, which 10% probability of accident in 50 years. Or you may use the resist the strongest earthquake. So we this is the last section of our lecture, which is on the use of probabilistic ground motion earthquake resistance of buildings. And this is the expected performance of building in modern earthquake resistant design codes. So there usually we provide two seismic design of parameters ground motion, which is one is DBE. DBE is design basis of earthquake, which is equal to 10% probability of accidents. But normal building will use this DBE, which is 10% probability of accidents. So this DBE is resist the design level of earthquake with damage which may or may not be economically repaired, but without causing extensive loss of life. And based on MCE is to resist the strongest earthquake shaking expected at the site without collapse, but potentially with extreme damage. So MCE is for 2% probability of accident, DBE is for 10% probability of accident. And for dams, there are a lot of based on my experience, this dams is quite sensitive for structure and very large structure, and can sustain a very loss of life is much more compared to buildings. So normally we are going to use a very strict of design code. So this normally in the project that I involved, we use this standard of ICO, International Commission for Large Dams. And typically these standard, we will use even more return period, which is 10,000 years return period. So for our low to moderate seismicity, we normally estimate the return period will be 10,000 years. So it is equals to, so we call 10,000 years as the maximum considered earthquake, the same name, but in terms of the percent of probability, is we use only at 0.5% probability of accident. And we also calculate for the SEE. SEE is for safety evaluation earthquake, which is equal to 5% probability of accident in 100 years, about 2,000 years return period. Then normally we design these dams for the exposure time of 50 years or 100 years. So this is depends on the how close the dams to the fault line. And then for bridge, this is we use a different type of code in order to design our bridge based on Eurocode 8 or IBC 2000 or H2. So that we measure the ground motion parameters. Either we use the DBE, the same as buildings, or equals to 10% probability of accident, or MCE, which is equals to 2% probability of accidents. But the exposure time for bridge is normally we tackle for 50 years or 75 years for bridge. And this is the philosophy. Okay, this is I think the last slide. Okay, philosophy of seismic resistant design for structures. So for minor earthquakes, we usually need to prevent the non-structural damage. Okay, minor earthquake, small earthquake 3, 4. So we try our best to prevent any non-structural damage. And if we have moderate earthquake, so we have to prevent our structure damage and minimize the non-structure damage. So moderate earthquake, normally we found some non-structure damage, but we have to prevent our main structure damage, column, beam. Okay. And for major earthquake, okay, the active or much bigger magnitude of earthquake, so we have to avoid the buildings from collapse, and we try to save more life. Okay, if we have the major earthquake. So I think that's the only last slide. So that's all for my lecture today. So I would like to thank you very much for listening to this lecture. Yeah,